Welcome to the 13th video of this course on quantum processing. The last time we talked about the approach of 9-qubit code by Shor. It was a nice illustration for single qubit error correction and also for 2-qubit case as we saw. Today is considered to be the last video for the general purpose quantum computation. But to conclude that, it's important to know that the quantum error correction procedures had some difficulties when quantum mechanics began to insert into the picture of information theory. The problems, or the main three problems, big problems that we had, is that the errors in the quantum world are continuous. So to correct them, to identify them even in a channel or a quantum noisy channel, it's a big problem, and it takes a great deal of effort, maybe infinite resources that you can invest in this to identify. And also for the measurement, to let you know that the quantum measurement completely destroys or kills the state. So if you have a density matrix or a psi state, you can actually, when you measure this, make strong projective measurement on this state, the state is completely dead, actually. And another problem, and this is the title of this video, is the no cloning feature in the quantum world. No cloning is very interesting because it serves a lot in cryptographic protocols that you can build. Why it was a problem, but all of these difficulties were solved. But the scope of this course won't cover the continuous error treatment and the no cloning. They were solved by entanglement, but this destructive measurements that we already encountered the solution for this part of destructive measurements by measuring the effect on the environment, and we saw that in the system operation for the system environment model, and also for the operator sum representation. We also encountered this solution, but the solutions for continuous errors and no cloning we won't recover in this course. But let me just tell you what is no cloning theorem tells us about. So no cloning means that simply we cannot copy a state. Okay, but what is the operation that happens when you copy a state? If you copy a state, you have some unitary evolution, unitary transformation on a qubit, for example, psi, and you have 0. And if you'd like to copy that, you would end up using the operation here, getting you psi A and also psi B. You copy A on B. Okay, an example of this, you can copy you can copy 1 on 0 and you would have 1. Classically, in the information theory part, this is accessible. You can copy whatever information you'd like to measure, and you can trace them out and try to see different things in the information world, but the quantum mechanical perspective of this says no, you cannot clone it. Because if you can clone it, it means that if I want to clone, if I would like to copy a state minus, and the basis of minus here, a minus state here, it means that I copy it on 0, I have two minuses here, which are tensored, and if you'd like to get it for yourself, tensor minus with minus, and you will get this result. Okay, keep this result number 1. So let us trace it more carefully. Okay, if I have this state, unitary transformation of the state, I can expand that by their basis, 0, minus 1, okay, and multiply it by the cat vector here, and you will end up having 1 over square root 2 of u acting on two tensored state, and also 1, 0, 0, 0, and 1, 0. If this is truly right, it means that I have the operation that affects 0 and 0 will get me 2 zeros. As I copy 0 on 0 will get me 2 zeros. And if I copy by unitary transformation, if this is true, I copy 1 on 0, it gets me 2 1s. Like this. So 0 on 0, 2 zeros, and 1 on 0, and 1 1. So if this is again right, it means that if I calculate this state carefully, try it for yourself, and you will end up having this result. And this result number 2 is not the same as number 1, as you saw here. So this is not the same as number 1. So there's a problem. The problem is that you cannot copy a state. This procedure is completely wrong. You cannot operate or unitary transform your state in the quantum world and getting this state again copied in another basis. So this conclusion is just a quick conclusion that if you prepare a qubit, okay, in the quantum world, if you prepare a qubit, please note that your qubit is truly precious. So you have to preserve it for a while because it's really expensive. And this confirms the idea, this is the beginning of quantum cryptography. If you'd like to go for quantum cryptography, the first thing that you learn is that you cannot clone a state. You cannot clone a quantum state because of the no cloning theorem that we encountered here. So make sure that your qubit is preserved, specifically when it's an entangled state. So it takes a great deal of effort to prepare that in the lab. The next videos will be devoted for the quantum simulation, how you can do special purpose quantum computation, which is the quantum simulation part, and we will start to review some basics on quantum optics, some atomic physics, to start out our journey, another journey, the second journey of this course, which is quantum simulation. Thanks, and see you again in the next set of videos.